1st of July, NASA detected a mysterious object.
A nuclear-powered spacecraft sent by aliens.
3I Atlas was an interstellar visitor.
In 2017, a tiny shard from another star cuts across the sky. Astronomers name it Oumuamua. But by the time instruments lock on, it is already moving away. Too faint and too fast for clear answers. Years later, another interstellar object is detected. It's not faint or fleeting. It is larger than its predecessors, brighter than any object ever confirmed from another star, and it refuses to go unnoticed. That object is ATLAS, and it forces astronomers to rethink what interstellar visitors really are. The first shock. It all begins on October 19, 2017. The Pan-STARRS telescope in Hawaii flagged a faint, fast-moving point of light crossing the sky. At first, it looked like an ordinary asteroid discovery, the kind astronomers mark down by the hundreds each year. But within days, orbital calculations revealed something extraordinary. This object was not looping around the sun in an ellipse like every planet, comet, or asteroid born in our neighborhood. Its path was hyperbolic, an open curve that proved beyond doubt it had come from outside the solar system. That made it the first known interstellar visitor ever detected. Astronomers gave it the Hawaiian name Oumuamua, meaning scout or messenger from afar. The choice fit perfectly. It was a cosmic envoy, slipping into our system at a steep angle, slicing past the sun and racing back out to the stars. But the details that followed made it even stranger. Observations showed the body was unusually elongated, with some estimates suggesting it was 10 times longer than it was wide. Its brightness varied wildly every few hours, meaning it was tumbling end over end as it sped away. Unlike familiar comets, its surface reflected light in a deep reddish hue, suggesting space weathering over immense spans of time. The oddest part, though, was what Oumuamua did not have. There was no coma, no dusty halo, no tail streaming behind it the way comets do when ice turns to gas in sunlight. Yet its trajectory betrayed a subtle push, a tiny, non-gravitational acceleration that could not be explained by the pull of the sun alone. Something was nudging it, but the usual suspects were missing. Theories multiplied as quickly as the data vanished. One proposal suggested it was made of hydrogen ice, and that invisible hydrogen gas venting off the surface could give it the small thrusts observed. Another argued it might be a nitrogen shard chipped from the frozen crust of a Pluto-like world. Some models suggested it was a fractal, low-density clump of dust with unusual reflectivity. And hovering over all the natural explanations was the idea that drew the most public attention. Harvard astronomer Avi Loeb's suggestion that it could be a solar sail, a thin, flat craft pushed by sunlight, the kind of technology human engineers are only beginning to test. That possibility was enough to send Oumuamua into headlines around the globe. For the first time, the phrase alien probe was discussed not in science fiction, but in peer-reviewed debate. Even years later, the arguments have not been settled. The hydrogen ice model gained traction after a 2023 paper suggested that venting could explain the acceleration, but others argue the conditions needed for such an object to survive interstellar travel are implausible. In the end, the problem was simple. Oumuamua was discovered too late and was too small for the world's telescopes to gather the kind of information needed to solve the puzzle. By the time the biggest observatories were turned toward it, the object was already fading into the distance, its faint light lost in the background of stars. The data set we have is frustratingly thin. What remains are models, speculation, and arguments that still divide astronomers today. Oumuamua was the first shock, the opening chapter that forced the scientific community to accept that objects do arrive here from other stars. But it left almost everything else unresolved. It was a reminder of how little warning we had, how quickly mysteries could appear and then vanish, and how unprepared we were to make the most of such a rare encounter. A familiar comet. On the morning of February 15, 2013, people across Chelyabinsk, a city in Russia's Ural Mountains, saw the sky light up. A streak of fire cut across the atmosphere, brighter than the sun for a few long seconds, before a shock wave shattered windows and injured more than 1,000 people. The culprit was small by astronomical standards. A stony meteor, just about 20 meters across. Yet its arrival was enough to send hundreds to hospitals and cause millions of dollars in damage. And nobody saw it coming. That event was a wake-up call. Scientists knew the solar system was filled with debris, rocks, ice, and metal fragments left over from planet formation. But Chelyabinsk showed how blind humanity still was to smaller, fast-moving objects. The meteor had approached from the direction of the sun, making it invisible to ground-based surveys until it was too late. It slipped through every layer of early warning systems, and when it exploded, it shocked a world that thought near-Earth space was at least partially under surveillance. The lesson was obvious. Our sky was far from secure. If something bigger came, the damage could be catastrophic. Within months, international efforts to track dangerous objects picked up speed. One project in particular grew out of that urgency, ATLAS, short for the Asteroid Terrestrial Impact Last Alert System. ATLAS was designed with a simple but ambitious mission: scan the entire visible sky every night and catch anything moving that didn't belong. Funded primarily by NASA and developed by the University of Hawaii's Institute for Astronomy, the system began operations in 2013. Its telescopes weren't enormous, but they didn't need to be. What mattered was speed and coverage. Each ATLAS unit could scan the entire sky in a single night, using wide-field cameras to capture countless faint streaks and points of light. Software would then sift through the images, identifying which specks of light were stars, which were artifacts, and which were genuine moving bodies. At first, ATLAS consisted of 2 telescopes stationed on Hawaii's volcanic slopes, one at Mauna Loa and another at Haleakala. But as funding expanded and the system proved its worth, the network grew. By 2022, new telescopes in South Africa and Chile were added, giving ATLAS global reach. Now the system could scan both northern and southern skies, ensuring that nearly every region of Earth was protected by its nightly sweeps. The network could detect objects as small as 100 meters across, with days of warning and even smaller bodies, like Chelyabinsk-sized meteors, with hours to spare. ATLAS's purpose was planetary defense, spotting potential impactors before they struck. But in the process, it also became a sentinel for anything unusual. Its nightly scans were sensitive enough to detect faint comets, asteroids, and, as fate would have it, objects not bound to the sun at all. ATLAS had put humanity in a position to spot something extraordinary. That extraordinary moment came sooner than many expected. In late August 2019, just 2 years after Oumuamua had shocked the world, an amateur astronomer in Crimea named Gennady Borisov spotted a comet through his homemade telescope. Unlike Oumuamua, which had baffled scientists with its strange, dry appearance, this new visitor looked familiar from the start. It had a bright halo of gas, a coma, and a trailing tail of dust. Its spectrum revealed the usual signatures of water vapor, carbon-based molecules, and other chemicals common to solar system comets. This new object was soon designated 2I/Borisov, the 2I marking it as the second interstellar object ever detected. Its orbit was hyperbolic, like Oumuamua's, meaning it had originated from beyond the sun's gravitational hold. But in every other respect, it behaved like a normal comet. Its chemistry mirrored what astronomers were used to seeing. Its brightness curve followed predictable rules, and its dusty coma showed that the same processes shaping comets here were likely happening in other star systems as well. Borisov was the baseline. It proved that interstellar visitors weren't all exotic mysteries. Some were ordinary snowballs, shaped by physics we understood. That contrast was crucial. If Oumuamua was the outlier, the strange messenger with no clear explanation, then Borisov showed us what normal interstellar debris looked like. By the time the 2020s arrived, scientists knew that interstellar objects weren't once-in-a-lifetime oddities. They might be rare, but with the right tools, they were detectable. Atlas had proven itself as a global watchman, and a new observatory was preparing to push the boundaries even further. In Chile, the Vera C. Rubin Observatory was finishing construction. With its massive mirror and wide-field camera, Rubin would be capable of detecting thousands of faint objects every night, including interstellar wanderers that had previously gone unnoticed. The stage was set. Humanity had gone from blind surprise in 2013 to bewilderment in 2017 to cautious understanding in 2019. And in 2025, the payoff arrived. Atlas, the survey system born from Chelyabinsk's shockwave, spotted the most remarkable visitor yet. The biggest visitor yet. On July 1st, 2025, the Atlas telescope at Rio Hurtado in Chile recorded a faint moving speck. At first, it looked like countless other objects the system routinely flagged. But the next day, orbital calculations confirmed what many suspected. This was not a local comet or asteroid. Its orbit was hyperbolic, proving it had come from another star. The International Astronomical Union gave it the designation 3I/ATLAS, the third confirmed interstellar object in history. Unlike Oumuamua, which had been discovered on its way out, this object was caught on its way in. That timing made all the difference. Astronomers would have months to study it as it approached, passed perihelion, and then departed. For once, the scientific community could observe an interstellar body in real time, not just scramble for fading scraps of data. Early observations suggested something else remarkable. This visitor was enormous compared to its predecessors. Based on brightness estimates, astronomers concluded it was between 9 and 12 kilometers wide, making it larger than both Oumuamua and Borisov combined. For perspective, it was roughly the size of a small mountain. With more mass came more material to study, more gas, more dust, more opportunities to learn. Its behavior, too, was intriguing. From the moment of discovery, 3I/ATLAS displayed a coma and a faint tail, signs that it was actively shedding material as sunlight warmed its frozen surface. This made it more like Borisov than Oumuamua, a true comet rather than a dry fragment. Yet its trajectory carried surprises. It was inbound from the direction of Sagittarius, near the galactic center, on a steep hyperbolic path. Its velocity relative to the Sun was already about 37 kilometers per second, 133,000 kilometers per hour, and it would only accelerate as it drew closer. By the time it reached perihelion, its closest approach to the Sun in late October 2025, it was expected to be racing along at nearly 160,000 miles per hour, twice the orbital speed of Earth. Crucially, its orbit posed no danger to Earth. At closest approach, it would remain well beyond Mars's orbit. never coming closer than about 1.4 astronomical units from the Sun, roughly 130 million miles. That safe distance meant astronomers could study it without fear, treating it as a laboratory sample passing through rather than a threat on a collision course. The timeline was clear. July marked the discovery. Through August and September, as it moved closer to the Sun, it would brighten enough to be imaged by professional and advanced amateur astronomers using large telescopes. In October, during perihelion, it would be hidden in the Sun's glare, unobservable from Earth. Then, in early December, as it swung back outward, it would reappear for another round of observations before fading into the dark. By mid-2026, it would be gone, racing back into the void of interstellar space, never to return. This predictability was what made 3I/ATLAS revolutionary. With Oumuamua, scientists had days. With Borisov, they had a few months. With Atlas, they had nearly a year of preparation and data. Observatories around the world coordinated schedules, planning spectral analysis, photometric monitoring, and even space-based imaging. Missions like ESA's Comet Interceptor, though not ready in time, were suddenly more urgent. If another interstellar visitor was spotted years in advance, humanity might finally meet it with a probe. Atlas was more than just another visitor. It was a milestone, a turning point in how science approached these rare messengers. For the first time, the community had both the warning and the tools to study an alien body in depth. Oumuamua had been strange. Borisov had been familiar. But 3I/ATLAS was something different again. Big, active, and caught in time. What Atlas reveals. Once astronomers confirmed 3I/ATLAS was real, the next question was simple. What exactly is it made of? With Oumuamua, the lack of a coma meant chemistry remained hidden. With Borisov, spectroscopy showed ordinary cometary gases, cyanide, diatomic carbon, and water vapor. Atlas promised something far richer. Early spectra revealed the fingerprints of water, carbon monoxide, and carbon dioxide streaming from the surface. On first glance, that made it resemble icy bodies in our own Kuiper Belt, the vast reservoir of frozen objects beyond Neptune. But closer inspection revealed isotope ratios that didn't quite line up with solar system standards. This was a body forged under different conditions, shaped in a different star's nursery, and now passing close enough to dissect. It was like a planetary sample jar delivered across light years. Telescopes quickly mapped its coma. Hubble measured the faint halo of gas and dust surrounding the nucleus, and by late 2025, the coma stretched an astonishing 8,000 miles wide, nearly the diameter of Earth itself. Dust ejection speeds were higher than predicted, suggesting strong jets of sublimating material blasting off the surface. But those jets refused to behave normally. In places, the outflow looked directional, like nozzles firing. To some, it was simply exotic outgassing. To others, it looked eerily like controlled thrust. Chemistry deepened the puzzle. Observatories reported carbon dioxide levels far above what solar system comets usually display. More startling was the nickel anomaly. Spectra from the European Southern Observatory showed clean nickel emission lines, with almost no accompanying iron. That should not happen. Nickel and iron are forged together in the hearts of dying stars and appear side by side in meteorites across Earth. To see nickel without iron defied every cometary model. Some astronomers proposed exotic explanations. Maybe this fragment came from a supernova remnant, or maybe radiation had stripped one element more than the other. But others pointed out that plating a surface in nickel or driving jets with engineered chemistry would produce exactly the same signature. The tail added yet another layer of strangeness. In physics textbooks, comet tails always stream away from the sun, pushed back by radiation pressure and solar wind. But multiple teams noticed that Atlas's tail sometimes bent forward, pointing sunward as if resisting the flow. Calibration errors were ruled out. The orientation shifts were small but persistent. Some called it noise. Others whispered about active steering. Even the light curve refused to settle into routine. Photometry teams at M1T and Hawaii tracked its brightness night after night, expecting a smooth increase as sunlight vaporized surface ice. Instead, they logged sudden jumps, 10-minute spikes that looked like flashbulbs in deep space. The flares repeated at near-regular intervals, brightening, vanishing, then brightening again. No comet known in the solar system behaves this way. Dr. Angeli Ralph described it like a lighthouse beam sweeping across the dark, a burst of energy followed by silence, then another burst. Natural theories included rotating metal-rich patches or unusual venting patterns. But once more, the possibility of an engineered signal was difficult to avoid. Every fresh measurement fed the debate. Was this a natural comet showing us a chemistry and behavior not yet catalogued? Or was it a probe, a machine disguised as a snowball? For every anomaly, there was at least one natural explanation. For every model stretched to the breaking point, there was a voice suggesting something more. What nobody doubted was scale. 3 I/ATLAS dwarfed both Oumuamua and Borisov, offering more material to measure, more data to parse, and more chances to confront the uncomfortable. It was a cosmic experiment too large to ignore, and the results were challenging our expectations at every turn. The implications. Beyond the numbers, ATLAS raised sweeping implications. First, it confirmed what scientists had begun to suspect. Our solar system is porous. We are not sealed off. Interstellar debris cuts through our neighborhood whenever gravity nudges it our way. Atlas was only the third confirmed case, but its size suggested that countless others might pass unnoticed each year. Some astronomers estimate thousands of interstellar fragments could be drifting through at any given moment, invisible to our current instruments. With surveys improving, those invisible wanderers may soon appear. The Vera Rubin Observatory in Chile, already scanning the night sky with unmatched depth, is expected to find 1 to 3 interstellar objects every year. Instead of rare once-a-decade anomalies, they may soon become routine discoveries, each carrying new chemistry and new mysteries. Atlas, in that sense, may be less an exception and more the first in a steady parade. The practical implications extend further. Agencies like ESA and NASA are no longer thinking only of observation. ESA's Comet Interceptor, scheduled to launch in 2029, is designed to wait in space and then sprint to meet an unexpected visitor. Atlas arrived too soon for that mission, but its discovery has already sharpened the urgency. NASA engineers have begun sketching intercept concepts, rapid launch probes that could chase down the next interstellar traveler. If Atlas had been discovered a few years earlier, a spacecraft might already be en route. Next time, we may not miss the chance. Planetary defense also looms over the conversation. In 2022, NASA's DART mission deliberately smashed a spacecraft into an asteroid, proving for the first time that humanity could nudge a rock off its path. That was a controlled test, a proof of concept for deflecting local threats. But what if one day the danger is interstellar, arriving at 150,000 miles per hour? Atlas posed no threat, but it reminded us that objects from deep space can and will cross Earth's orbit. Preparing for that possibility is no longer abstract. The anomalies sharpened the stakes. Transcript D's leaked MIT dataset suggested course corrections embedded in the raw telemetry, residuals too regular to dismiss. The nickel-only chemistry stood apart, resistant to every standard model. The deceleration profile looked smooth, as though guided. Pentagon analysts even considered the geometry of its flyby, noting that its line of sight crossed Earth's orbit 3 times at night-side alignments perfect for observation. To defense planners, that looked less like coincidence and more like reconnaissance. None of this is proven. Some scientists argue strongly that outgassing and exotic compositions explain everything. Others see patterns that feel less like nature and more like design. The debate is unsettled and may remain that way until a probe intercepts one of these objects up close. What Atlas has done is force that conversation out of the fringe and into mainstream scientific halls. The public has been pulled into the mystery as well. Within weeks of discovery, a grassroots network called Project Watchtower organized online. More than 18,000 amateur astronomers worldwide began logging sightings, uploading light curves, and sharing spectra. From deserts in Australia to rooftops in Europe, backyard telescopes joined the hunt. The effort echoed Project Moonwatch of the 1950s, when citizens tracked early satellites across the sky. Back then, the fear was Soviet surveillance. Now, the wonder and worry centers on something not of this Earth. Myth has always shadowed science in the sky. Ancient civilizations told stories of wandering stars and omens from above. As Atlas bent its tail against the wind and flashed bursts of light into the dark, those old stories felt less like relics and more like echoes. Folklore and physics briefly overlapped, as if the questions we ask today are not so different from those asked centuries ago. In the end, ATLAS's legacy may be twofold. Scientifically, it delivered the richest trove of data ever gathered on an interstellar body, enough to challenge models and stretch theories. Culturally, it reminded us that the cosmos is not quiet and not sealed. Rocks, snowballs, and perhaps even probes cross the gulfs between stars, and we are finally learning to see them. Oumuamua left us baffled. Borisov reassured us with the familiar. Atlas now unsettles us again, forcing us to wonder if the line between comet and craft is thinner than we imagined. Oumuamua was the strange scout, fleeting, mysterious, and gone before we could understand it. Borisov was the baseline, a comet in disguise that showed us interstellar visitors can look familiar. But Atlas is different. It is not small, not dim, not vanishing in a matter of weeks. It is big, it is bright, and it is staying long enough for the world to study in depth. For the first time, scientists can follow an object from another star system step by step, watching its chemistry, its light, its path, and its secrets unfold in real time. Every spectrum and every image carries the possibility of rewriting what we thought we knew. And whether the final answer proves ordinary or extraordinary, Atlas has already forced us to expand our imagination of what is possible. And it may be the one that demands we rewrite the story of astronomy itself.